When we take a spring, something that we are so familiar with now, and the spring has length L in a relaxed state, spring constant K, I can extend the spring with some force that I apply. The spring then will counter it with a spring force, and it will be in equilibrium there. I call this the zero position, and let's call this now delta L instead of X, what we have done before. If I double the force, delta L will double. Hooke's law says that the force is linear with delta L. In other words, delta L is proportional with F. Nothing new, as long as Hooke's law holds. If I make the spring twice as long, I would get double the extension. Because when I have two springs in series, each one under influence of this force will get longer by this amount. Since I have two springs in series, I will get twice delta L. So delta L is also proportional to the length of my spring. If I take two springs parallel, one like so and one like so, relaxed length L, both the same spring constant K, and if now I apply a force on it, then each one of these spring forces is only half this one. Together they counter this force. In other words, the extension delta L that I obtain from this external force is now only half as much as it would be with one spring. And if I had three springs parallel, all identical, I would only get 1/3 of the extension for a given force. In other words, delta L is also inversely proportional to the number of springs that I have, assuming that they are identical springs. Now I'm going to use a rod or a wire which has cross-sectional area A and length L, and I'm going to apply a force here. As a result of that force, it will get longer by a certain amount, delta L, exactly like the spring. And clearly, when I make this force stronger, delta L will increase. And as long as Hooke's law holds that the spring force provided by the rod balances this out, provided that the spring force is linearly proportional with delta L, I have again that delta L will be proportional with the force. Double the force, I get twice delta L. If I put two of these rods together, so I double the length of the rod, then clearly I will get twice delta L, because each rod will experience the force, each rod will get longer by delta L, and so two rods will get longer by 2 delta L. So again, delta L is proportional with L. Suppose now I have two of these rods next to each other. Notice the parallel with the two parallel springs here. And I apply a force F. Then the spring force on each one of them, if I call that the spring force, will only have to be half to counter this force. So they both have a cross-sectional area A. And so now, with double the cross-sectional area, I get only half of delta L. And so now we have a situation that if I made a rod whereby this was 2A, just one rod, which is completely equivalent to this situation, I'm only getting half delta L for a given force. And so now we have that delta L is proportional, inversely proportional to the cross-sectional area of the rod. So now we can make up the balance, and we can say, aha, delta L is proportional to the force, proportional to L, and inversely proportional to the area, the cross-sectional area. So F divided by A is then proportional to delta L over L, and that proportionality constant we give a name, and that is capital Y, and that is called Young's modulus. So this is Young's modulus. F over A, which has the dimension of pressure, force per unit area, is what we call stress. And delta L over L, which is dimensionless, we call that strain. If we compare two rods with different values of Young's modulus, then the one with the smaller value of y for the same stress will give you a larger strain. In other words, it's easier to make it longer. If Young's modulus is very high, then the rod is extremely stiff, then it is very difficult to make the rod longer. I have here for you some numbers, which of course are on the web, so you don't have to copy them. And you have Young's modulus there for various metals, and I also have it down there for nylon, and today we will work with that quite extensively. We could first do a simple example, just to get a feeling for what is at stake here. I can take a rod with a radius r, which is 0.5 centimeters. That would give me a cross-sectional area of 8 times 10 to the minus 5 square meters. So GA thick, the rod. I make it very simple. I make the length 1 meter. And I hang on the rod at the bottom a mass M, which let's say is 500 kilograms. Do I want 500 kilograms? Yes, I want 500 kilograms. In other words, the force which I pull on the rod is about 5,000 newtons. So I can now ask myself, how much longer is this rod going to be? So we're going to have that delta L is going to be F divided by A times L divided by Young's modulus. And we do know what F is, we know what L is, and we know what A is. So in our case, this number is 6.3 times 10 to the 7th for the numbers that we have. And so now we can look at steel as an example. So we take steel, Y is 20 times 10 to the 10th newtons per square meter. And we substitute that in here, and we find that we get an extension delta L, which I believe is only 1/3 of a millimeter, indeed. 0.3 millimeters. Think about this. A steel rod, a centimeter thick, and it has a length of 1 meter, and I hang 500 kilograms on it, and it only gets longer by 0.3 of a millimeter. You couldn't even see that. However, if you go and make the rod, which would be really a rope, if you make it out of nylon, which has a Young's modulus, oh, well, it's 55 times lower. I don't have to use that number. It's about 55 times lower, so the delta L will then be 55 times larger, and so instead of 1/3 of a millimeter, I will get something like 17 millimeters. And that you can see with your naked eye. I take a rope, yay thick, of nylon, I hang 500 kilograms on it, and I will see it gets longer by 1.7 centimeters. You can see that right in front of your eyes. If I start adding more weight on these bars, then very interesting things are going to happen, as we will discuss today. One thing which is obvious that will ultimately happen if you keep loading down, keep adding mass, it will break. And the breaking point is given there in the 3rd column, and we call that the ultimate tensile strength. So when F over A, when this value becomes too large, that's what it comes down to, then it will simply break. If we take the case that we have here, the steel rod, for which F over A is 6.3 times 10 to the 7th, because L is 1, remember, then you can look there under steel, that it wouldn't break. We would be very safe, because it wouldn't break until F over A becomes 5 times 10 to the 8th. And so we're a factor of 10 away from that. There's no problem. Even nylon would be very safe, because that wouldn't break until the stress is 3 times 10 to the 8th. However, if we chose aluminum, if we made the bar out of aluminum, then you're very close to this number, 6.3 times 10 to the 7th. And so if you add a little bit more mass than 500 kilograms, your aluminum bar would break. So you see the properties of these metals are very, very different indeed. Now, before it breaks, we reach a situation that the strain is no longer proportional to the stress. In other words, we abandon Hooke's law, as I will show you also today with a demonstration. The material begins to deform. It begins to flow in a way. And when you take the weights off, it will no longer have its original length. It will not return to the original length, but it will be much longer. And I will try to sketch you here